All right, so 8.3, simplifying radical equations, expressions. I'm messing up already. Simplifying radical expressions. So we talked about this a little bit already. If I have, well, what we have, let's do it like this. Yeah. If I have the cube root of a to the 12th, I know that cube root can be rewritten as 1 over 3. So that means all I have to do is divide that 3 into the 12. You know, if you want to keep going with the process, that's 12 over 3. And that'll just be a to the 4th. So that's what we're looking at doing here. But what if this number right here is not divisible by 3? So let's say if I have the cube root of a to the 17th. So what you would do is look, or let me say look, let's say find the largest number So I want to find the largest number divisible by the index of the radical. And of course, we're talking about this 3 right here. That's the index of a radical. So the largest number, and I probably should say under 17, the largest number under 17 that's divisible by the radical, or the index of the radical, is going to be 15. That's the largest number under 17 that's divisible by 3. And I will break up my exponents that way, or with that in mind. In other words, 15 is the largest number that I can pull out of that 17 that's divisible by 3. So I use that number, and then what is left will be set aside. So you see I have 8 to the 15 and then a squared. 15 plus 2 is still 17. Haven't changed the value of anything. But now I can break this up into a to the cube root of a to the 15th times the cube root of a squared. There should be a cube root in there. Now I can simplify this piece. That'll just be a to the 5th. 3 divided into 15. Then I leave the other piece, or the other part, under the radical. And this would be my most simplified way of expressing that answer. All right, questions before we try another one? All right, here we have the square root of p to the 5th, q to the 9th. So don't forget the index here. When you don't see anything, it's 2. They assume you know it's a 2 there. So the highest exponent or highest number under 5 that's divisible by 2 is 4. Highest number under 9 that's divisible by 2 is 8. So the way I would break this up is do p to the 4th, p to the 1st power, q to the 8th, q to the 1st power. 4 plus 1 is still 5. 8 plus 1 is still 9. And I put what I can take the square root of, on the one radical, and then what I cannot take the square root of in the other radical. Divide the 4, 8 by 2, that'll be p squared, q to the fourth, and then the square root of pq. Questions on that? Do one more. Fourth root of x to the 15th, y to the 28th. So that will go to x to the 12th. I can take the square root of x to the 12th. I can take the square root of y to the 28th. Let me write it like this. All right. So I broke up the 15 into 12 and 3. The y to the 28th is divisible by 4, so I don't have to break that up. Remember, we're asking ourselves what's divisible by this number right here at 4, the index of your radical. So the 12 and the 28 goes under here, and we leave x cubed over there. Divide each exponent by 4. We have x to the 3rd, y to the 7th, and x to the 3rd under the 4th root. All right. Questions? Any questions? All right. Let's see. Another way we could be given a scenario, we can do that same thing to numbers. Let's see if I had just the square root of, I don't want to, let's go square root of 18. Can I take the square root of 18 evenly? But I can break it up into numbers and use a number that I can take the square root of. And look at the factors of 18. I can break it up into 9 times 2. I'm using 9 times 2 because 9 is a perfect square. Square root of 9 is 3. And then you leave the 2 under the radical. Same thing with 500. Break it up into 100 times 5. Doing that because you can take the square root of 100. And the square root of 100 is 10. And you leave the 5 under your radical. All right, here we have the cube root of 250. So now you need a perfect cube. Before we used 100 because 100 was a perfect square. That's because we're dealing with square root. Now we need a perfect cube. And that would be 125 times 2. So the cube root of 125 is 5. And you leave the 2 under that radical. All right. So now we're looking at the cube root of 81y to the 17th. And once again, our thought process is to have what we can take the cube root of, what we cannot take the cube root of. So we're going to do it like this. We can just go ahead and set it up. Now looking at 81. 81 is 3 times itself 4 times. So I can break that up into 3 times 27. 27 I can take the cube root of. The 3 I cannot. And now we're looking at the 17 and saying what's the, I think we did 17 already as far as the cube is concerned. Largest number under 17 that's divisible by 3, and that'll be 15. So it's y to the 15th, y to the second. So the 15 plus 2 gives you your 17 back. Cube root of 27 is 3. Cube root of y to the 15th is y to the 5th. And that's the cube root of 3y squared. All right, question before we look at that next one. All right, so once again, breaking it up into what you can take the fourth root of, and this time what you cannot take the fourth root of. So when we look at it, 48, we're talking about taking the fourth root. So we're looking at 16 times 3. Yep. 16 times 3 will give us that 48. And 16 is 2 times itself 4 times. Then we will go looking at our exponents, trying to see if they're divisible by 4, then great. If not, what's the highest number under that number that's divisible by 4? So I'm going to break up that p to the 9th to 8 plus 1. Q to the 10th would be 8 plus 2. And I can divide that 4 by 4, so I can leave that as a part of what we can take the fourth root of. So the fourth root of 16 is 2. And then fourth root of p to the 8, p to the second. That's q to the second, r. And then we leave the other stuff under the radical. All right, so here we have the cube root of 16x cubed y to the 9th over 2x cubed y to the 12th. We can simplify this first, which will make it a lot easier to deal with. 16 divided by 2 is 8. X cubed over x cubed actually cancels completely. And then here, don't forget when you look into your exponents, you're subtracting your exponents. So that would be the cube root of 8y to the negative third power. Cube root of 8 is 2. Don't forget you're dividing this into this. So that's going to be y to the negative first power. Then you can simplify it by bringing y down to your denominator. It's 2 over y. All right, let's look at another one. Try to cover multiple scenarios that you may see in your homework. All right, so what we have here is 4 times the square root of 48 over 24. This 4, I mean, yeah, well, I could say just 4, but this 24 mainly can simplify with what's dealing with what's going on with the 4. It cannot deal with anything under that radical. So just making sure we're clear. There's not anything under this radical that can affect this 24 until it comes outside the radical. Okay, so if I wanted to simplify where we are before I look at what's under the radical, this 4 can simplify into the 24 and leave you with just 6. 24 is 4 times 6. So now we're looking at the square root of 48 over 6. Now I can break up the 48, talking about what I can take the square root of, what I cannot. is 3 times 16. Square root of 16 is 4. Now I can simplify one more time. There's a 2 that's in both. That can cancel out. Leave you a 2 on the outside and a 3 on the bottom. And that would be your final answer. Once again, that 3 under the radical cannot be affected by the 3 under the radical as far as simplifying is concerned. You cannot cancel out those 3's. Either both will have to be under the radical or both will have to be on the outside of the radical. So here is an example of both terms being under the radical. So I could rewrite it this way and then cancel out. 27 divided by 3 is 9. A's cancel. And then b cubed over b is b squared. Square root of 9 is 3. And the square root of b squared is b. Any questions? Any questions? Yeah, same thing. Okay, questions before we look at 8, 4. Let me see, did I put title? Yeah. Just adding, subtracting, multiplying. Yep. All right, so 8, 4 is adding, subtracting, and multiplying these radical expressions. So whenever I want to add or subtract these radicals, I have to have, let me see, for adding and subtraction. Yep. So radicand is the thing that's under the radical. So our radicand here would be y. So in order to add and subtract fractions, you need the same index. We talked about the index before. That's what's right here. What's in what comes right before the radical, I guess you would say, or right there in that little crevice of the radical. So you need the same index for your radical, and you need the same radicand. And your radicand is what's under the radical. So we have 6 square root of y plus 4 square root of y. The answer will be 10 square root of y. But if anything is different, I cannot add them together. So in other words, if I have 6 square root of y plus 4 cubed root of y, I can't add them. If I have 6 square root of y plus 4 square root of x, can't add those. So if the index of your radical is different or the radicand is different, then you cannot add those expressions. All right, so if I have 9 square root of 3 minus 6 square root of 3 plus 5 square root of 5, the only ones that I can combine, it's just like combining your like terms. The only ones that I can combine are these two. So 9 minus 6 is 3. That's square root of 3 plus 5 square root of 5. Once again, we're talking about adding and subtracting. So then they give you one like this, fifth root of 5b plus 5b, and you would just write cannot be simplified. Because one has the index of 5, the other one does not. It has the index, it has the index of 2. Oh. All right, so now here, before you can make the declaration that it cannot be done, you have to simplify as much as possible first. So you know that the radicals, the index of your radicals are the same. So you try to simplify the 28 and the square root of 28 and the square root of 175 first to see if you can manipulate the problem to make those radicands the same. So you want to simplify as much as possible. Now, if the index of the radicals are different, like we had here, then there's nothing you can do about that. Just go ahead and write that you cannot. But we want to break this up. So let's look at them individually. Square root of 28, I can break that up into 4 times 7, because I can take the square root of 4. That'll be 2 square root of 7. All right, next one, 125, I can break that up into 25 times 7. So that's 5 square root of 7. All right, questions before we go back to our original problem. All right, so that's going to be 4 times 2 square root of 7. Let's do it like this. Plus 3 times 5 square root of 7. So we just took the pieces that we broke down and put them back into the original problem. So that'll be 8 square root of 7 plus 15 square root of 7. So now we have the same indexes on our radicals, or the same index on our radicals, and the same radicand. So now we can go ahead and add these together. 8 plus 15, 23 square root of 7. Questions. All right, let's do another one. So here we have 7 square root of 8 minus 3 square root of 27 plus 2 square root of 72. All right. So let's look at breaking down each one. So we don't know what we can add or subtract from each other and what we cannot add or subtract from each other because, you know, we have these different radicals that need to be broken down. We need different colors for each since I have colors at my disposal. Go blue here. All right. So the square root of 8, I can break up into 4 times 2. Square root of 4 is 2. Leave the other 2 under the radical. Square root of 27. Break that up into 9 times 3. So that would be 3 square root of 3. And 72 square root of 36 times 2. Square root of 36 is 6, 2. All right, questions with the breakdown before we plug them back to our original problem. All right, so that's 7 times 2 square root of 2. I think it was minus, right? Yep. Minus 3. 3 square root of 3 plus 2 times 6 square root of 2. It's 3, 2, 7. So 7 times 2 is 14. Minus 9 square root of 3 plus 12 square root of 2. All right, so combine the like terms. So it's 14 plus 12, which is 26. Square root of 2 minus 9 square root of 3, and that's where we stop. All right, one more example like this, just in case a variable is involved. So if a variable is involved, then we have to include the variable as well. Remember, if let's say if one has x, the other one doesn't, just like terms, you cannot add them or subtract them from each other. So here, looking at our expressions, we need to simplify as much as possible under that radical. So we have a times square root of 45 minus 5 times square root of 125a squared. So square root of 45, I break up into 9 times 5. That's 3 square root of 5.
So you have to put the A on the inside? Well, oh, that's 125. I apologize, sir.
Oh, okay. All right, cool. So you cool. Okay. All right. So the next one, the 125 a squared. We can break that up into 25 a squared times 5. 5 times 25, give me that 125. And I can take the square root of a squared evenly. Square root of 25 a squared is 5a. You leave the other 5 under the radical. All right. So we got a times 3 square root of 5, 5 minus 5 times 5a square root of 5. So that'll be 3a square root of 5 minus 25a square root of 5. So now we have same index, same radicand. and same variable. So you got to have all three in order to be able to add them or subtract them. And subtracting that would be negative 22a square root of 5. All right, so here 3 square root of 5 times 7 square root of 2. And when we're looking at multiplying, we don't have to have the same index. Well, I take that back, we don't have to have the same radicand. So what we can do is just multiply what's on the outside and multiply what's on the inside of the radicals. So that'll be 21 square root of 10. All right. Here, square root of 12 times square root of 28. We can multiply what's under the radicals, or we can simplify first, then multiply. The reason why I would probably suggest simplifying first is because multiplying what's under the radicals may give you a number that you're unfamiliar with, when you are more familiar with 12 and 28, and they'll be simpler numbers to process. So I would say go ahead and simplify these first. So the square root of 12 can be broken up into 4 times 3, which would be the square root of 4, which is 2, and you leave your 3 under your radical. Square root of 28 is the square root of 4 times 7. Take the square root of 4, that's 2, leave your 7 under the radical. So now we're looking at 2 square root of 3 times 2 square root of 7. 2 times 2 is 4. Square root of 3 times square root of 7 is 21. All right, here we have the cube root of a squared, b squared, times the cube root of 54, a to the 4th b squared. Now here, since I can't simplify this any, I will go ahead and combine it with this expression over here. Remember, whenever you're multiplying like basis, all you're doing is adding your exponents. So multiplying these together will give you the result of 54 a to the 6th b to the 4th. So now we can break it up. So the 54 you can break up into 27 times 2. Because we're looking at what can we take the cube root of. That's a factor of 54. And the 6th power is divisible by 3. So I'll use the whole a to the 6th. b to the fourth, I will break up into b to the third and then b to the first power. 3 plus 1 is 4. But now this whole expression right here is divisible. Or you can take the cube root of. I'll say it like that. Cube root of 27 is 3. A cube root of a to the 6 is a squared. Cube root of b cubed is b. And then you leave 2b under the radical. All right. Couple more scenarios and should be good. All right, so here the cube root of, or we're going to multiply the cube root times the quantity of 3, cube root of 3 minus 4. So we're talking about just your normal distribution process. So the cube root of 3 times 3 to cube root of 3 will be 3 cube root of 9. You just multiply what's under the radicals. Then the cube root of 4 is 4 cube root of 3. Cube root of 9 is 3. I keep saying cube root. Square root of 9. If I say cube root up here, I was wrong. Sorry about that. Square root of 3 times 3 square root of 3 minus 4. I think I kept saying cube root, but that's square root of 3. And then 3 square times the square root of 9 minus 4 times the square root of 3. Square root of 9 is 3. So this simplifies to just 3 right here. And there's nothing you can do with 4 square root of 3. To finish it off, 3 times 3 is 9. And that'll be your final answer. All right, one more. So we have 9 square root of 2 minus square root of 3 times square root of 2 minus 5 square root of 3. So we would do our binomial distribution. So 9 square root of 2 times the square root of 2 is going to be 9 square root of 4. So 9 square root of 2 times 5 square root of 3 is going to be 45 square root of 6. Can y'all hear me? Everybody good? Yeah, I got kicked out for some reason. All right, so let's go back to share my screen. All right, so where was I okay with this distribution? Did y'all hear me as far as this?
I didn't hear that part.
Okay, so all I said was 9 square root of 2 times the square root of 2 is 9 square root of 4. Then 9 square root of 2 minus 5 square root of 3. Just multiply 9 times 5, which is 45, and then 2 times 3 under the radical, which is square root of 6. And here, negative 3, square root of negative 3 times the square root of 2, which is negative square root of 6.
So you said multiply the 9 times the square root of 2?
Yeah, we have 9 square root of 2 that we're distributing into this other parentheses over here. That was the first step. So 9 square root of 2 times the square root of 2 gave me 9 square root of 4. You only multiply what's under the radical.
Basically doing 4.
Yes, Yep. We're doing our same binomial distribution. Yep. Just doing it with the application of your radicals. And then for that last one, negative square root of 3 times negative 5 square root of 3. So that'll be a positive 5 square root of 9. So square root of 4 is 2. That gives us that. And then negative 45 square root of 6 minus square root of 6. Don't forget there's a 1 in front of there. So that would be 46 square root of 6. And that's going to be plus 5 times 3, because the square root of 9 is 3. All right, that'll be 18 plus 15. So that'll be 33 minus 46 square root of 6. All right. Questions on anything that I've mentioned? Anything. All right. We have some minutes left. Coley,
Yes.
I know you have some questions about that review.
Yes.
What number did you want to start with?
I wanted. I don't have my textbook ebook open,
Okay.
but I wanted to start where we left off at, but I don't.
Hold on 1 second. I got kicked out of. We know when I got kicked out. I think Connect Math let me go too. Let me log back in.
I'm trying to figure out how to minimize this.
I am pulling up the review now. All right. All right. So I think we were like at 17. I know it was in the back.
Thank
Nope. Yeah, no problem. I think we had got past that. I think we were looking at complex. I think we were here. Now, if you want me to do 17 or 18, let me know. But I think we were.
17, 18.
Say again?
We can do 17 or 18.
Okay, let's see which one.
Because
Yes,
what I plan to do after we got out of class today is go back through them. I think you can still practice, right?
Yeah, you should be able to, yeah.
Right? Go back through them again, and hopefully tomorrow retake the test.
Okay. So let me take this one. And you want to see 19.
If we have time, 19 through 21.
Yeah.
I appreciate this, Professor.
Yep, not a problem. So let's look at 17, and then we'll look at 19 through 21.
You still want me to talk through what I see?
Yeah, sure. You can start us off and see what your strategy would be. All right, so there we go. We got 13 over 5k squared plus 7k plus k over 5k plus 7 equal to 1 over k. All right.
That first expression, 13 over 5k to the second plus 71 plus 7k, I will factor out the k. I rewrite it as 13k parentheses 5k plus 7. Second expression I rewrite is k 5k plus 7 equals 1 over k. Now, you taught me if I see an equal sign, I don't worry about the denominator being the same. I take my LCD and multiply it to all my numerators.
You're right. You got it.
So I take 13 times k, 5k plus 7 over k parentheses 5k plus 7 plus k times it's to be k, right? K times k parentheses 5k plus 7 equals 1 parentheses k times 5k plus 7.
Yep.
Over k. I'm not worried about I'm not concerned about my denominator because of the equal sign.
Right.
So I take 13 times 5, I get 65.
Hold on. Don't forget to cancel, though. Remember, the purpose of doing that is because they're going to cancel.
Oh.
And that's going to leave you with just k.
Wait, okay. I got to cancel now. Let me rewrite 5k plus 7. Okay. I got to cancel out the 5k plus 7. And the other the 5k in the numerator and the 5k in the denominator, I got to cancel those out. It only leaves me with 13 over k plus.
Hold on. Did you say 13 over k?
Yes.
No, the k canceled out as well.
The k canceled out as well.
Yep.
13 times k parentheses 5k plus 7. Both k's cancel out. 5k plus 7 cancel out. That only leaves me with 13.
Right.
So 13 plus k to the second. Wait, hold on. The 5k cancels out with the 5k plus 7. That only leaves me k to the second. Equals, that 1 needs to be multiplied to that k. So that's 1. I'm still going to come out with k parentheses 5k. Wait, hold on. 5k to the second.
Well, remember there was a k in your denominator.
K in the denominator, so they got to cancel out.
Right. And that leaves you just 5k plus 7 on the right side.
5k plus 7. I'm still hiccuping. I'm still making mistakes. Reorder the problem. K to the second plus 13 equals 5k plus 7. I got to set it to 0.
Yep.
So I move everything over. It'd be k to the second minus 5k minus 7 plus 3.
Plus 13.
Plus 13. So,
you're fine.
All right. So -5 minus 7. Well, I can't touch those. -7 plus 13. 6. So to the second minus 5k plus 6. Then I factor
Yep.
that. I use the AC method. That would be 3 times 2, or negative, let me see. The center number has to be negative. I have to do 6 times 1.
Now, your back number is positive. That means your signs are going to be the same, though.
So it has to be -6 times -1.
But that will give you a -7 in the middle. So you would use -3 and -2.
-3, -2.
Yep, because when you add -3 and -2 together, you get -5.
So k squared minus 3k minus 2k plus 6. Factor out the k, that leaves k minus 3. -2, factor out the -2. That leaves k minus 3. I have k minus 2, k minus 3. My set numbers are +2 and +3.
Mm-hmm.
You see, I'm still hiccuping.
Yeah, man. But you're still alive. You can't hiccup if you're not alive, man. You're doing all right. Let's see. Let's look at those complex numbers. But questions on what we did. You good?
Yeah, we good. Basically, once I get my numerator, I still got to cancel stuff out in my denominator.
Mm-hmm. All right. So here we have r minus 6, 5r, 3r minus 18 over 45. So here we have one solid fraction or rational expression over one solid rational expression. When we have that, we can rewrite it this way.
But I got to remember to flip it.
Yep. Whenever you're dividing your. Now, notice I hadn't flipped it yet.
But this is where I get confused at, Professor.
I'm listening.
Which ones that we don't flip?
The only time what are you talking about when dealing with this type of problem?
Yeah, I remember one time we didn't flip.
Okay, it depends on what method you're using. So now here, that's why I was saying that if you have one solid fraction over one solid fraction, you can do this.
You flip.
Yeah.
You don't flip. That's why I'm getting confused at.
Well, we haven't gotten this. This is one scenario, sir.
Okay.
We'll get there. But let's take care of this problem.
Go by what I see.
Yep.
All right. Equals r minus 6 over 5. I'm writing this down, folks. Divided by 3r minus 18 over 45. Rewrite r minus 6 over 5r times 45 over 3r minus 18. You already worked it. Okay.
All right. So now, once you factor it out as much as possible, you want to cancel out with whatever is common, top and bottom.
So let me write down what you got.
And I just decided to break down the 45 to all the way down to prime numbers.
So basically, you have to keep factoring.
Say that again. You broke up.
You have to keep factoring.
Yes. So that r minus 6 will cancel. 5 will cancel. And then one of those 3's will cancel. And you're left with 3 over 1, which is just 3.
That's what I have problems with trying to solve. So basically, you have to keep breaking down your whole numbers.
Mm-hmm.
And once you break them down, you cancel them out.
Yep, with whatever's in common with the top and bottom.
See, I would have did that wrong. Can you
Hmm.
scroll back up? I would have found a common denominator of 45 and multiplied 45 to the top fraction and the bottom fraction.
As long as you do it right, that's the second method. If you do it right, you still get the same answer eventually. But yeah, that wouldn't have been the most efficient method for this setup though.
This method one, right?
This is method one. What you're referring to is method two.
See, that's why I get the stuff twisted.
Well, like I said, method two would have worked. I'm just saying I just showed you the most efficient way
Okay.
to take care of this problem. So now the LCD would have been 45R. If you would have multiplied both top and bottom, well, when I say top and bottom, both numerators.
I wouldn't have known to put the R there.
Yeah, because you need it though, because R is right here. You see what I mean?
So this way is better. See, I wouldn't have known to put the R there. I would have just put 45.
Yeah, yeah. Not using that R would have made you come up a little bit short because, whenever you multiply the numerators, because you're going to multiply the numerators by the LCD, which is what we'll do in the next example, you're trying to cancel out your denominators, just like we did here. You multiply the numerators by the LCD so we can cancel out the denominators.
And with this method, can I recite back to make sure I got it in my head, Professor?
Let me say this. Class is 10:48, so if you have somewhere to go, then you feel free to dismiss. I'm going to finish working this out with him, and then I'm going to roll on to my next class. So have a great weekend, be safe, and I will see you on next class. All right, what you got, sir?
What if I see it like this in fraction form? Rewrite it like with the divide sign.
Mm-hmm.
Flip it. Uh,
And then factor.
after I flip it, factor it.
Mm-hmm.
Then after I factor it, cancel out even more.
Yep, cancel out what you have in common.
So stick with what method is this again? One?
This is method one.
Method one then. So I'm getting it messed up in my head.
Mm-hmm. So let me show you when method two would be more efficient to use.
A fraction over a fraction.
All right, so here we have 12 minus 5 over 3x, and then 5 over 12x minus 3. So notice we have a different setup here. We have separate terms. We have 4 separate terms. These are not combined as one term or one fraction. On the last one, we had one solid fraction over one solid fraction. That's when method one is most efficient. But when you have separate terms, then method two is the best one to use. When you find the LCD of each denominator. So the only denominators that we have are 12x and 3x. So the LCD is 12x. Because 3 can divide into 12 and so can 12. 12 can divide into 12 itself.
So how would I write that on the thing? I put it outside on parentheses 12x, right?
Yes.
See, the way I do it, I make a big parentheses.
Mm-hmm.
So the 3 divided into 12.
Mm-hmm.
That leaves me with 4x.
Now, don't forget we have 3x down there. So the x is supposed to cancel out as well. So that's what should happen.
Hold on,
Hmm
I got a little lost. So 12x divided by 3x leaves 4x.
No, 12x divided by 3x leaves 4. Not 4x, because the x cancels out as well.
Wait, hold on.
Hmm
I see 12 minus 5 over 3x.
12 minus 5 over 3x. The 12 is not over the 3x. The 5 is over the 3x.
Yeah, the 5 is over 3x.
Uh-huh.
Now, if I would put the 12 on the outside
Mm-hmm.
in the numerator, top part of the problem, it'd be 12x times 12 minus 5 over 3x. And
So, so now let me ask you this. Are you looking at the way I've written it?
yeah, I'm looking at it. It's just I'm not seeing what you're seeing. I'm,
So, let's take it one term at a time.
all right.
12x times 12. So
All right.
nothing cancels out there. Then we're looking at 12x times 5 over 3x. And so the 12x divided by 3x cancels out completely, leaving you with just 4 times 5.
Oh, you took the 12x and multiplied it to each term.
Yes.
Oh, man.
Yep. That's how you would do it.
So the 12x would go to each term in the top part of the numerator.
Mm-hmm. And then to each term in the top part of the denominator.
So it'd be 12x times 12.
Yes.
See, I was thinking you'd take that 3x and cancel out the other 12x. You see where I was going with that? And
Yeah, now you can't do it because they're not together. You know what I mean? Like this minus sign separates your terms. They're two separate terms. See,
oh,
now if it was written like this with 3x over under both of them, then that's different.
oh, Jesus.
And 12x cancels out completely here, leaving with just 5.
So for me to break it down, I got to compartmentalize each section that 12x goes to each individual.
Mm-hmm.
Where you get that 20 from? Go back with that 4.
Mm-hmm. The 4 that was left.
Both x's cancel out from each other. That leaves 4.
Mm-hmm.
4 times 5 equals 20. Then that leaves me 144x minus 20. And I'm done, right?
Well, got to see if anything can be factored. When you look at your GCF, possible GCF out of their first 2 terms or the top 2 terms, you can take out a 4. That's 36x minus 5.
Then I got to do a -1 on the outside.
Yep, you see it.
So my answer would be negative.
Mm-hmm.
-4. Oh, I would have got that wrong.
What you mean?
I would have made it -4. Wait, hold
Yeah,
on.
that's what it's gonna be. You can pull the negative out of the top or the bottom. It doesn't matter. But you're right. That's what it would be, -4.
Those cancel out. My answer would be -4.
Uh-huh.
I wouldn't have got this by myself, Professor.
Well, that's why it takes a little practice, sir. There's a little bit of practice.
I damn sure we got this wrong on the test.
Well, I got 4 minutes till my next class.
Well, what I'm gonna do is go ahead and go back through each problem through the practice today.
Okay.
And tomorrow tomorrow's Friday, am I correct?
Yes.
I'm gonna log into Proctor again, see if I can take the test again.
Okay.
If I can score higher, and because I'm getting behind on radicals.
Mm-hmm.
That's it. I was burnt out on section 7.
Yeah, I can imagine, sir. I can imagine. Trust me, I get it.
Listening, I know you're not a counselor, but I appreciate you letting me vent on this.
It's not a problem, man.
Thank you, Mr. Tucker.
All right, no problem, sir.
We're gonna be
And
seeing each other again for pre-cal and applied calculus. So
okay.
I want to keep it consistent because you know what I'm strong in, what I'm weak in.
Mm-hmm.
So if I got you for pre-cal and applied calculus, you already know what I know and what I don't know.
Gotcha. Yep, not a problem, sir.
You have empathy and compassion, like he don't know this stuff.
But yeah, man, you're gonna be all right.
Thank you, Professor Tucker, and I thank you for taking the time after class to help me.
Yeah.
Thank you. I really appreciate that.
Yeah, man, no problem. Not a problem at all. Let me know how you do on that test.
I will. As soon as I take the test, I fire off a not text message, email,
Mm-hmm.
and let you know. I just got to score higher, and that's it. As soon as we get off the computer, I'm going to log in to connect and start doing the practice. Finish it up, then do the practice. And sorry for being long-winded. Talk to you later. You got to go.
All right, man. Take care.